First, I would like to introduce historic examples of shellfish byproduct valorization, because this is not really new. As you can see here, the scallops shells are present in our culture, in Galician culture mainly, and related with circular economic examples from more than 1,000 years ago. In fact, in the Códice Calixtino related with the Santiago's Way, the Camino de Santiago, and the Pilgrims Pact, you can see examples and the name of the scallops there. And here, for instance, the scallop shells has been used for several purposes for valorization under a circular economy concept. For instance, here in Galicia is a typical use these scallops for musical instruments, also from ash rights to recollect the tobacco ashes in typical cafes in coastal areas in Galicia. Also, it's used for cooking because you usually cook the scallops in the shells and you serve it in the shells. As traditional use in agriculture, the people use the shells for amendment to the soil, because here in Galicia we have acidic soil, and they use the shells, crushed shells, to be used as fertilizer on the soil. The pilgrims used it for drinking utensil, and also you can see here a chapel that is in an island here, Isla Leticia, and it's used as construction material. As you can see here, this chapel has plenty of scallop shells in the walls of all of the chapel. But also regarding the past uses of the shells from mollusks, they have been used in construction in many coastal settlements around the world. You can see that in the Senegal, in the Salon Delta, they have examples of shells in construction as far back as 5,000 years ago, or more than that. Also, the tabi, that is a form of concrete made by treating shells, creating a mixture with lime, sand, water, and ashes, as well as the broken shells, are used from the middle centuries. And you can see examples of this the type of constructions in Florida, Georgia, Carolinas, both South and North Carolinas, but also in Spain or South England. Here you can see an example of this tabi construction. Normally, the tabi consists in lime, shells, and sand in equal amounts, and a little bit of ashes, mainly wood ashes for the recipe. But this construction is not very solid, because this is not resistant to the fires, or is not really useful for construction today. Another past uses are related with medical uses, medicinal uses, but not medical uses indeed, because are mainly like amulets to help maintain the health, the fertility. And you can see examples in Egypt to where these amulets is like functional jewelry or something like that, that promote good health at the people that wear it. Regarding the jewelry, the mollusk shells has been really intrinsically linked with the jewelry through the story. In fact, the oldest identified piece of jewelry in the world that was discovered in Israel was made from shells of the sea snail, the Nasarius gibosulus. And this shell dates back from 100,000 or 135,000 years ago. But the shells are being part of the jewelry today, because we have examples here in Galicia. It's typical to have jewelry, mainly earrings or a necklace related with the mussel shells that the people painted and use it for jewelry today. Also, regarding the past uses, there are examples. For instance, a archaeological site in Texas recovered more than 3,000 shell artifacts. The shell artifacts are important due to the potential for the shell strength and hardness that they explain. And also, for instance, in Australia, they use it for cooking pots or things like that. So it's important also as tool. But today, the current examples are more varied. And you can see here that in a report from a Cache project where they established the percentage of the different shells that are using in the different fields today. And you see here that the first one is related with the reef restoration and ecosystem services, accounting 70% of the total uses today. Also, the absorbent for water treatment are important, with means the 14% of the uses today. Also, some of them are ranging from 8 to 11% related with the pH and carbon dynamics, mainly for soils and agricultural supplements, also for construction in aggregates and mortars, for biomedical and cosmeceutical products, also as functional materials, as absorbent for gases, and as catalysts. And the historical uses that I have mentioned previously means around 5% of the uses today, as for instance, jewelry or something like that. Going in the current uses today, the livestock feed production is one of the most important ones. The calcium supplementation is the key point, because mainly the shells are made for calcium carbonate, and normally they are used for improve the health of the livestock, mainly related with the bone health of the livestock. Also in birds, mainly in hens, like in hens, they are used to supplement to improve the quality and the strength of the eggshells. This is a particular thing that here in Galicia we made every day, not, but all the times that we consume shell mussels or oysters, wherever, the people in the houses use them to go to the kitchen, to the chicken, sorry, and to the hens for use it to improve the quality of the eggs. Also, there are some references there that we have several studies that are show that they are really effective for bee supplement for broiler chickens. They have trying to replace the lime that are typically used for calcium carbonate supplements. And some of these studies show that the use of the shells improves the digestibility and the growth of the chickens. Another use are related with the agricultural liming agent. This is the second major market, and they includes neutralization of the soils, mainly for acidic soils, and for metals bioremediation. The liming is an important activity for improve the soil fertility, and normally also is related with carbon sink mechanisms to be a carbon sink in the agriculture field. The problem mainly is that the toxicity of the salt of the grass shells can be a problem, but in the studies that you can see here, a couple of references are not demonstrated that the salt could be a problem of toxicity. And normally they use crushed shells, not the entire shells, to improve this status of the soil, increasing, like as mentioned there, they promote several microbial populations, increase the nutrient cycling of the process. Also, another current use is as the ice grid. Normally, the chlorine-based compounds such as sodium chloride are the common rock salts using for the icing the roads. but these chlorine-based roads could damage the roads, and for instance, in the airports are forbidden because it damages the aircraft. And the use of calcium magnesium acetate or any calcium acetate, it's could be an environmental friendly potential alternative as be used for the ice circuit. This use the calcium of the shells as calcium donor for the formation of the calcium acetates, and could be another possibility of shells valorization, as was used in some cases in Japan for that point. One of the main uses is related with the water treatment, mainly related with the heavy metal removal in the wastewater treatment facilities, because the calcium carbonate is really good to be a lead solvent. And the use of mix of shells rich both in calcite and aragonite should be optimized for the heavy metal removal. Because not only is interesting to remove the lead, but also another heavy metals such as the calcium, as was studied in other works, such as the use of the invasive snail fish acuta, that could be good for the absorption of calcium too. And also the more than the heavy metals, this is interesting also to use the carrier shells to remove nitrate, sulfate, or phosphate from the wastewater. This was typical for aquaculture, and we show later the examples for the GAIN project that we made, but it's important to know that it could be interesting to use these shells as a material trying to remove the nutrients, mainly nitrogen and phosphorus, for the wastewaters of aquaculture in the RAS systems. And also we have some examples for the water purification. Normally they work with oysters. In the GAIN we work with mussel shells because are more interesting for us in Galician region. Regarding other current uses, we can see that the green roofing, you can see here that the use of ecosystemic services and that points in the cities are interesting, and the use of the shells can help with the neutralization, for instance, of acid rain, reduction of heavy metal contamination in the drainage water, and you can use both in extensive and intensive ways. But both are designed with the same principal layers: the vegetation, the growing medium, the filter membrane, the drainage layers, the root barrier, and the waterproofing membrane. Another uses today are related with the construction, as we see previously with the TAVI. The use of the shells in the construction are typical in some structure in coastal village, for instance, in China, also in Scotland. Some cases in France are studying the incorporation of crushed crepidula shells in the concrete mixes. And also here in Galicia, University of Coruña has been developing a project, the BioValvo project, trying to demonstrate the use of mussel shells for being included in mortars. And they trying to construct a house located in Mariñeiros in Coruña, mainly based with walls, floor, and roof, using around 75% shell material in the composition. This project, you can see here the publication, have 3 stages. The first one was try to assess that the material have no technical barriers to be used in the concretes, and they use that the conclusion of this first stage are that the mussel shells gravel was the best option to be used as fill material. In the second stage, mainly related with the lab test studies, they use different percentage, and they could see that the replacement of in the conventional aggregate for the muscle shells was the 25% percentage. And finally, they are working right now in the experimental building, trying to define the applicability and the energy performance of the building during several years. Another uses are related with the catalyst. The calcium oxide catalyst is really important in the chemical industry today, and this calcium oxide is formed with the calcination of the calcium carbonate. And the waste shells from aquaculture could be a low-cost source for calcium carbonate for the production of these calcium oxides. And oyster shells are shown to be effective heterogeneous catalyst in the conversion of soybean, for instance, soybean oil into biodiesel. And also in China, they have important they have a reference of use these freshwater mussel shells to be a catalyst for biodiesel. Another uses are the biomedical and cosmeceutical ones, and the most uses for that point are related with bone and tissue reengineering. The powder of the calcium carbonate act as substrate for a new osteoblast growth and secrete the bone. For instance, the NAC power from the oyster Pinctada maxima could act as scaffold in bone reconstruction for human jaw defects, demonstrated that is a possibility in bone engineering with the shells. Also, regarding the different uses today, the use of shells for functional materials. For instance, there are some articles highlighting the use of these shells in polypropylene and polymer composites. The waste blue mussel shells were used for filler, for calcium carbonate filler in the propylene manufacture, and so you can see also as functional materials. And finally, one of the main uses today are related with the ecosystem services, and the shells return to the marine environmental is a possibility. Try to promote the ocean alkalinization as a method for limiting the atmospheric CO2 increases, and also to limit the ocean acidification, acting the shells at pH buffer. The project Sequestrate try to apply this alkalization concept, and they have not really positive results because it's complex to use the shells for calcium for CO2 sequestration. So they are continuing with this research right now. And finally, regarding the main results of the game project, we use the shells for two applications. One are related with the use of shells as substrate for the production of seaweed seedlings. This was done for SHP, for Christian, that speaks after me. And they use the substrate, the shells as substrate for algae, for cultivation of nori seaweed. The typical Japanese seedling producers use around 200,000 oyster shells to cultivate the nori conchothalis for seedling production purpose, but here in Europe, no industrial nori production exists so far. And the preliminary cultivation experiments that came for the Southern Habsburg Park exhibits that the conchothalis could grow in 6 types of shells investigated. Here you can see the pictures of the experiments. Cockle, oysters, and blue shells were inoculated with the Porphyra umbilicalis gametotype. And the best results are related with the oyster shells that, the oyster shells deliver optimal results for growth. It did not happen with the other, with the mussel and with cockle because they are or fragile in the case of shells from mussel shells, but too small in the case of the cockles. And the other use that we promote in the game project for shells are related with the use of shells as biofilter medium in the RAS systems. In RAS, we have the different mechanical filters, the different points to trying to clean the water. And one of the points is the biofilter. The biofilter is mainly to remove the ammonium and also nitrate if the nitrification occurs, but mainly to remove the ammonium point. Normally, the usual biofilter media are plastic rings, like you can see here, and we wanted to see if we can use the shells as biofilter medium, trying to reduce the use of plastic in this industry. Here in the Mediterranean area, they have problems with microplastics contamination, and if we can avoid the use of plastic, it could be good. And also trying to promote circular economy in the aquaculture area, using the aquaculture shells as waste material to be used for a useful point in the biofilter. In Anfaco, we work with first of all, we make the biofilter design. Here in this slide, you can see the design of the filter. This was done to be we need 3 different biofilters. One to compare crushed shells and entire shells, and other to have the control biofilter medium with plastics. So we make 3 biofilters with this design. The structure are mainly made by metacrylate, and the useful volume was 10 liters. And we have a platform on the bottom to guarantee the stability of the filter. We have 2 mesh points to avoid that the mussels can go down in the biofilter media. And here you can see the biofilter reactors with the shells on the right side and with the plastic rings on the left one. We pump the media, the wastewater from the bottom to the up part, and we evaluate the elimination of ammonium, nitrate, and nitrate in the biofilters. Here you can see a picture. I think that this is better of the biofilters. Also, we need oxygen, and we promote it with the machine that we have on the right side to have oxygen enough for the nitrification purpose. We have run the experiments in 2 different periods. The first one it's 15 days, and the second one more than 175 days. The initial concentration of ammonia was 5 ppm in both cases. The HRT ranged between 15 to 20 days, and in the case of the second experiment, 1 day after the 120. We try in the first experiment, we use an inocula typical for aquarium, the Prodivio, that has different microorganisms for nitrification purpose. And in the second experiment, we try to use also sludge, but we need to use the Prodivio and also the BioS inoculant to reach good results. We studied different parameters, the pH, ammonium, nitrate, and of course dissolved oxygen that we guarantee to have enough for nitrification purpose. During the first experiment, in the first period, the startup of the biofilters needed almost 15 days. On the right side, you can see the comparison between the plastic rings, the crushed shells, and the whole ones. And after the second nutrient dosage, the biofilter filled with the plastic material needed around 15 days more than the mussel shells biofilters, both of them, to eliminate the ammonia. And the mussel shell biofilter show a sharp decrease in ammonia concentration and an increase in nitrate. You can see in red bars. And after the third ammonium acetate addition, the biofilter packed with whole mussel shells was the best one, but we needed to close this experiment at that point, and we don't have more results because we have problem with the pumping in this point, mainly related with the salts problems with because we use seawater in the experiments. In the second period, you can see here the results with the plastic rings. We have problems at the beginning with the startup using the sludge as inoculum. And you can see here that the ammonium cannot reach zero concentration. So on day 14, more or less, we inoculate with the ProDBU inoculum the reactors. And on day 58, also another vial of ProDBU was inoculated, and we reach a zero concentration of ammonium. But we cannot able to eliminate the nitrate from the experiment, and this was not good for recirculation systems because the nitrate is also toxic for fishes. So we decided to use another inoculum with a different microorganism trying to promote the elimination of nitrate. And we use the BioS inoculum. And we observed that in several days we can reach the zero concentration of nitrate. But in these plastic ring reactors, the increase in ammonium and nitrate happens from day 140 days on. This was mainly due to the control of the pH that I showed after that. But if we compare the plastic rings with the crushed shells, we have the same problems in both, for instance, with the inoculum. But once the BioS was inoculated in the crushed shell reactors, we can reach good results after establish the biomass on that, and we eliminate completely the ammonium and the nitrate in the shells reactor. Here you can see the difference between the plastic in blue ones and in green. You can see the pH for mass shells, and you see that in the case of crushed shells, the use of the buffer capacity of them can maintain the pH in good points between 7.5, around 7.5 more or less. But in the case of the plastic ones, the pH ranked from 6.5, 6.6 to 8.4 when we use a buffer. Because we need to use a buffer to control the pH of the plastic ring. So it was not good because we need to introduce a chemical compound in the system. And similar to the crash ones, the whole shells was performed good, but in the case of the whole ones, they need more time to establish the zero concentration on both nitrate and ammonia concentration. Also, we make a scale up of the system. In that case, it's a pilot scale system that we install in a company, in Grupo Tres Mares, that allow us to use real wastewater for an aquaculture company. But in that case, it's not seawater, it's fresh water. And as the concentration of the ammonium was really low in the water of this company, we add 5 ppm of ammonium acetate to guarantee the ammonium concentration. And we work with a hydraulic retention time of 1 day on that biofilters. And in that case, the initial idea was to study the phosphorus absorption, but we also have some data about nitrogen elimination. We have a feed with a concentration of 5 ppm of ammonia, and the removal efficiency for ammonia and nitrate was 100%. In the case of nitrate, because this pilot scale system has one denitrification system and nitrification one, the nitrification yields around 66%. In the case of phosphorus, because this was the main objective on that point, the shells also allows a phosphorus absorption close to 50%, going from 0.12 to 0.06 in the effluent. But we also studied the phosphorus elimination at lab scale, because we don't get really good results only from the pilot one. So in that case, we used 2 biofilters. In one of them, put the crushed massive shells, and in the other, we used the same quantity of calcite material for comparison purpose, because we wanted to differentiate between the use of calcinate material as a difference between aragonite and calcite minerals. And these filters run for 30 days with concentration of 10 ppm of phosphate. And also after this day 30, we added 1 gram to evaluate the elimination of high concentration of phosphorus over a 24 hours period. On the first case, you can see here that calcite material was better than the shells to absorb the phosphorus, running from 86% of phosphorus absorption in the case of calcite, and in the crushed shells, this value was 79%, but they are really high, much better than in pilot scale system. And in the 20 hours period, the removal was low, using 1 gram per liter at the beginning, and we reach around 32% in the mussel shells and 45% in the calcite filter. So the main conclusions of these GAIN biofilter trials are that the similar efficiency of shells, whole shells, compared to bioplastic filters in ammonia and nitrate removal, but reaching at lab scale 100% of elimination when we work with simulated seawater. Also, in the pilot scale systems, we reach higher removal efficiencies in nitrification, and also almost 70% in the nitrification ones, using only shells as biofilter media. And we conclude that the selection of the inoculum seems to be really important to promote both nitrification steps, not only the ammonia, but also the nitrate removal. Also, we need to take into account some considerations for economic and environmental purposes, since we don't need replacement of shells during the 175 days of operation. So we did not observe excessive biofilm formation. So the shell waste for this use could be minimal for aquaculture farm, and we produce a lot of shell waste here in Galicia. So this cannot be a really important point to valorize only the shells in that way, at least that the biofilter media can be extended to other wastewater treatment systems or for municipal or industrial wastewater treatment plants. Also, if we try to promote strict regulation regarding the discharge of the effluents, for instance, zero ammonia or nitrate values, that could be crucial for stimulating the development of this application in a commercial way. And the GAIN trials show that the use of plastic filters in biofilters is not necessary for the correct elimination of nitrogen, confirming that the mussel shells is a good alternative for filling material, but we need to evaluate that over longer periods of time at industrial scale, and also with lower ammonia concentration, because we work with high ammonia concentration to see the clear difference, and we should work with lower amounts. And thank you very much for your attention, and hope to be useful for you.